This is the church exercise. We're going to use this to go through the different runoff calculation methods. We'll do it in 4 parts, working on the same document, which you have available to you to take notes and fill in. At the end of all 4 of them, I'll ask you to turn in one summary sheet. You don't have to turn in the whole thing. But we're going to start with the rational method, and I have the document in front of me that I'll be drawing on. I have a spreadsheet over here with my calculations and some notes right here. When I do this in class, I have the students pick some numbers, so hopefully I can be consistent with the numbers, but if there's a inconsistency, let me know and perhaps I grabbed the wrong number off the notes or something like that. So what we have here is we have a development, and I just did it for a church, and we're doing it in central Pennsylvania. Again, you need to know where it is to choose the IDF curves and the rainfall values. So it goes from west to east, and it slopes that way. So it's very simplified. The site is 900 feet north to south, so it's 900 feet up down as we look at it, and then 1,500 feet east and west, divided into 2 parts, 900 feet like that, and then 600 feet in that part. Right now, the upstream up gradient part is woods, and the lower gradient part is pasture. The slope is 1% on the woods part and 0.5% on the pasture part. And so we're going to develop it. We're going to put in there a church building, and that's 200 feet by 400 feet. And then the rest of this will be lawn, and then this whole section to the right, to the east, will be paved. So we'll start with doing the rate calculated using the rational method. The 2-year 24-hour rainfall for this region is 2.88 inches. We'll need that for the NRCS method, but we're also going to use that as part of the calculation for the time of concentration for the rational method. Site is on soil type B. The rational method is Q equals CIA. We have the area. We're going to choose C based on the land use and the soil type. The I, to calculate that from the IDF, we need the D and the F. The F is specified by the regulation. The D is going to be from the time of concentration. So the time of concentration for a site, or a section of the site, is the time as we go across here. So if we have, in this case, we're going to have this time that has a certain land use, certain slope, and this time. And so the time of concentration is the time of the different segments put together. Also, turns out that if we have a long flow path, I don't know if you can see that, so the water is running down the driveway here, and you can see it kind of runs off into sheets, but then it wants to get itself into what we call a shallow concentrated flow, and then to a channel flow. So when I do the calculation for what's coming off the back part of my property up there, I need to make some guesses on how fast it's going during the different sections getting there. The runoff transitions from the sheet flow, just as kind of, you can see this in a parking lot, it'll be just kind of a sheet of it, but that after a little bit it'll start to break itself up into little rivulets, and that's shallow concentrated flow. Then after that it forms into channels. So we might have to break this up into a time of sheet flow and then a time of shallow concentrated, and then the time of channel flow. And we have methods to, in different documents, guidance documents, we have various methods to estimate these. The sheet flow, you're not supposed to use it for more than 300 feet. Now, some regulations actually, or in guidance documents, say only use it for 100 feet. So check that out in the area you're working in to see if they have a guide on that. And so here's an equation based on the Manning's equations. The Manning's equations, you have the Manning n, and this is the equation for estimating the time of concentration. So the Manning's equation, you can estimate the velocity. This goes ahead and flips it around. So we're going to use the time of concentration to choose the size of storm we're going to use, and we're going to use that to calculate the runoff and the flow. But wait a minute, but we need the flow or the depth or something to calculate how fast the... So this is a method where we take, okay, they say, okay, take the 2-year 24-hour storm, and actually the formula says the square root of that, and this will come up with an estimate of the time of concentration given the ground cover using the Manning's n, and then the length of it and the slope, and alpha is just a units thing that we plug in there. It's 0.007 if we use feet. So let's put our numbers in there. I'm going to use for the pre-development, the woods part, I'll use an N of 0.4 for woods light underbrush. Wait a minute, it's a factor of 2. That's a big deal. Yeah. So as I keep saying, there's a lot of uncertainty in these. So this is going to be 0.40. The length we're going to use for the first 300 feet is going to be 300. The slope is given for the left-hand side of that as 0.01 or 1%. Now careful with that. Some of these formulas, they have you put S in as percent, so you'd put 1 instead of 0.01, which I find confusing. And then the number given for the 2-year 24-hour storm is 2.88 inches. So we calculate that, and I'm going to my spreadsheet, and my calculation of that says 72 minutes or 1.2 hours. So that's just for the first 300 feet of this. And then let's do shallow concentrated flow for the next 600 feet of that. And that's allowable. And for that, we also have another empirical equation somebody came up with, where the velocity is equal to 33 times k times the slope, where we can pick k off a table here. And I'm going to use a k of 0.076. Where did I get that from? Forest with heavy ground litter. So that's the k I'm going to use for that. 0.076. And if I plug that in there, that goes to the velocity equals 0.25 feet per second. Time is 600 feet. So 300 feet with the sheet flow, then 600 feet with the shallow concentrated flow over 0.25 feet per second equals 2,400 seconds equals 40 minutes or 2/3 of an hour. And then we'll use the same equation on the east side of the site. I'm going to choose a k of 0.213. So this was the k here, 0.213. Why do they give us 3 digits when there's so much uncertainty in this? I don't know. But that gives me a velocity of, I'm looking at it, basically 0.5 feet per second. And then a time would then be, that's also 600 feet for that section. 0.5 is 1200 seconds. Those 20 minutes. I should have left more room on here. So our pre-development time of concentration, we have 72 minutes, 1.2 hours in the woods. We have 40 minutes that's the shallow concentrated flow. Then, no, sorry, that's the sheet flow. And then 40 minutes at shallow concentrated flow. And then 20 minutes on the right side of things. So a total time of concentration of 132 minutes equals 2.2 hours. And for post-development, I'll show you my spreadsheet here. I'm going to use an N of 0.15 for that, and that's for, I pulled that off of Short Grass Prairie, I think I used for that. For the shallow concentrated flow, for the sheet flow, the shallow concentrated flow, I'm going to use 0.47 for grassed waterway for the first part of it, and on the right hand side I'm going to use 0.619 for paved. So remember, the right hand side, we're going to pave it after that. So I do the same calculations. I put in the velocity and then calculate the time from that, and I get 33 minutes for the sheet flow, 6.6 minutes for the rest of it shallow concentrated, and 6.9 across the pavement. So let me move back over here and write the numbers in here. So we have, this is 33 minutes, this is 6.6, and this is 6.9. This was actually 32.8, so that comes up to 46.3 minutes, which is 0.77 hours. So in a few minutes we'll use those times of concentration to come up with the I values for our Q equals CIA. Let's calculate the C value to start with. So what we need to do is calculate a composite C value. So in pre-development, we have two sides here, the woods and the pasture. Now it's the same length this way. This way is 900 feet of the woods and 600 feet of the pasture out of the total of 1,500 feet. So I'm going to use that to say that it's the woods, there's 9/15 of woods and 6/15 of pasture. For the woods, I'm going to use a C value of 0.10. I actually got that off a different table than the one that's below there. And for the pasture, which again is 6/15, I'm going to use a 0.30. So the composite, the weighted average of those, is 0.18. So that's the pre-development C value. For the post, I have the lawn/roof, and then I have the paved. So the paved part, that's going to be 6/15 of the runoff coefficient for the parking lot. We're going to use something like it shows below there in that table, 0.85. For the lawn/roof, we need to do another kind of weighted average of that, where we take the roof is impermeable, then we have the lawn, or I'm actually going to take 9/15 and I'm going to go with a 0.2 for lawns and heavy soil for that. So maybe we want to do a little more refinement on that. It might depend on how we treat the runoff from the roof, from the gutters, but that composite comes out to a 0.47 post-development C. Okay, that's the C. We have the A, we need the I for the Q equals CIA. The pre-development, let's do this for the 100-year. We probably have to run our spreadsheet for one up to 100-year, but we're going to do it for the 100-year. Then the duration is from the time of concentration is, for the pre-development, it's 132 minutes. For the post-development, we'll again do the 100. The duration, I'm going to use, what was our number again? 46 minutes. 46 or 47 minutes. In my notes, actually, I have, from doing this in class, I have 3 different numbers there because I had 3 different groups of students choose the numbers for the K values and stuff in the time of concentration. So they came up with 3 different numbers. So as I keep saying, there's a lot of uncertainty and variation in anything with hydrology. So what is my I? To that I have to go to an IDF curve, or this I have a table here. So I have, this is the frequency estimate 90%. So the for the 100-year storm, we need the 2.2 hours, or 132 minutes, and we have 2 hours. 100 years is 3.55, so we go 3.6. Well, what is that? Hold on. That's 3.6. Oh, this is, so these should be getting, for intensity should be getting lower because it's going to rain real intense for a short period. It's not going to rain that intense for a longer period. So these are totals. So it's 3.8, 3.6 for 2 hours. So I'm going to say 3.6 over 2.0. I said 2.0. That 3.6 was from, well, 2.2, 2.0, 2.0 equals 1.8 inches per hour. If we had more data or curve, maybe we could make a difference between the 2 hour and the 2.2 hours. Post, we want 46 minutes. So it's going to be like halfway between between 2 and 2.75. We'll go with, I don't know, 2.4 inches, 3.6 inch per hour. This is 2. What did I just say? Inch per 0.77 hour, and that comes out to 3.1 inch per hour. So what we're looking for is the Q. Q equals CIA, and then so the pre equals our C was 0.18. Our post, it was 0.47. 0.18 times 1.8 inch per hour times the area of, this is right at 31 acres, the whole site. It's 43,560 square feet per acre, and that comes out to 10.04 acre inch per hour, which is equal to cubic feet per second. The post-development is Q equals 0.47 times 3.1 inch per hour. So it rains harder because of post-development? No, it doesn't rain harder. We're doing this for a shorter period of time. So shorter duration is higher intensity. And that, again, times 31 acres equals 40. No, let me check that. Equal 41.5 cubic feet per second. So the difference is equal to 31.5 cubic feet per second. So let me write that up here. Pre was 10.0 cubic feet per second. Post was 41.5. So the difference was 31.5. And so that's what we have to handle, that flow, and we can't let the post-development run off our site any faster than the pre-development did. So we could route it, the hydrograph, through a retention bond or something, but just kind of get a concept of that. This is not really how you do it, but let's calculate how much water must be stored to hold the difference between the pre and post-development storms for the post-development time of concentration duration. So that 46 minutes of the post-development design storm, if we multiply 31.5 cubic feet per second times 46 minutes, we come up with 87,000 cubic feet. 7,000 cubic feet, which is right about 2 acre feet. So to hold that in a 1 acre retention pond, we'd need 2 feet of depth of that. That doesn't sound like much for the 100-year storm, but that's what my calculations say. So that's the rate control, the peak rate control. We can't let the post-development run off any faster than the pre-development. Now we're going to also have to cover our volume control, that we can't let the post-development volume be any more than the pre-development volume. And to do that, we'll use the NRCS method. So that will be our next step in here.